and then apply background. Here I am. All right. So spectroscopy, we are going to learn. This is also an analytical technique, and it is a very powerful analytic technique. And this technique, actually, you will see in widely, almost everywhere for this analytical process. You will see it, and this is a non-destructive process. I mean, some of them, not all, but some of them are non-destructive, like UVVs that we will be doing is non-destructive, and AAS that we will see in a bit is a destructive process. What I mean by destructive and non-destructive is I will describe when I go there. But for today's aims, learning objective for this our lecture today, yeah, to know or describe or understand the principle, okay, how this is spectroscopic analysis thing works. Or, I mean, actually spectroscopy, you understand that from the name it implies that spectrum, that means different spectrum of light. So we use that spectrum or light to do the analysis from it. And then the applications of this spectroscopy, in which field or to find out what we use this type of analytical technique. And of course, when we can use this or apply this, how can we analyze the data or to identify and to quantify? Identify means to know the identity, right? What is what? Whether it is a compound A or compound B or compound C, what is that? Identify. And then how much of this compound A or compound B or compound C is there? Is 50 gram, 5 moles per liter? What is the, I mean, how much is there? So that is the quantification that we will know also. Of course, we have to do the calibration to know the quantity or quantification, but we will go there as an example we'll see later on. So now, since we are in week 6 and we see that we have covered all the analytical chemistry, I mean, at least the majority of it, not all everything, but majority of it, the analytical chemistry. So we started with the gravimetric analysis. We have seen it, how the gravimetric works. So I'm sure that you know what is gravimetry. And then from there, we have seen the volumetric. After that, it's the volumetric analysis of the samples. Okay. And then those are the destructive. I mean, if you use that sample for gravimetric or volumetric analysis, you cannot take the sample back and use it for your own cause. So that is destroyed. That is why it's a destructive process. And then we came to instruments, whereas we saw that chromatography, different type of chromatography, paper chromatography, and then column chromatography, HPLC, GLC, and how to use those things to find out identity of a chemical, and then to quantify the chemical we have found out. And then we have seen the spectroscopy. All right, now we are going to see the spectroscopy. So the instrumentation will be done by this analytical technique. Okay, so what is spectroscopy? As I said or mentioned before, that the light interact with the matter. How does the light interact with the matter? I'm sure that many of you has this question to yourself, that why do we see different colors, right? Why there are so many different colors that we see it? Why all of them are not the same color? So this is one thing, and because the light, how the light interacts, or maybe more precise way to say that how the light bounced back from one's the object, and that is why we see the color. And if the light, actually, when we say light, the light that we see, it is a form of an electromagnetic radiation, right? It's a form of electromagnetic because it is a wavelength of some energy coming through a wave, and then that is the thing that we see is a light, although it has a photon character, but we will consider it here as a waveform. So this wave, when it is coming and then hitting some, when it is coming, the waveforms of what I said just now, that light coming as a wave light. So it carrying some energy with it. When it is coming as a wave, it is carrying some energy, and then that with that energy, when this wave is hitting to something, of course there will be similar and opposite reaction, right? According to Newton's theory. So it is actually, this is how it is interacting, and this energy that carries the energy in a particle form is known as photon. It's complicated, but let's say that light is coming as an waveform. For our case, we are seeing it as a waveform. And actually, the energy of the photon can be counted or can be calculated using this equation. That is the very famous equation which Einstein got the Nobel Prize. All right. So the range of wavelength and frequency in light is known as electromagnetic spectrum. So the wavelength and different frequencies, the electromagnetic spectrum is divided on those things. Now, this from this part until this part, right? So this is the whole spectrum of light. But usually we understand light means whatever you can see. Beyond our visibility, at night, we don't call it light, right? Because there is absence of this type of the light, the spectrum that we can see. There are some wavelength, but that is what we cannot see, or our eyes cannot see. So the wavelength started from 10 negative 16th, all right, 10 negative 16 nanometer to 10 power 8 meter. So this is very big wavelength, and X-ray, gamma rays to long radio waves. These are the what do you call it? The range of the spectrum. Out of this whole range, there is only a small bit from 400 to 700. To be more precise, 380 to 720. So this is the nanometer of wavelength is only visible to human eye, to our eye. We only can see anything when there is the wavelength of that electromagnetic radiation is between this range. So like this is the wavelength, right? This is the wavelength. From here until here, if it is 400 to 700, only then we will be able to see the wavelength. Now, okay, so using those things, using this light or electromagnetic spectrum, we can use it for many other purposes. Not only for looking or seeing an object, also by doing some kind of experiment, and also we are doing it to do our medical purposes. We use it for medical purposes. So X-rays, many of you, we know that X-rays, right? IR, radiation. So nowadays, IR is, I mean, quite. We see a lot of IR instruments around us, the motion sensor or whatever, and then microwave. So these are the things that we use for NMR, right? For the diagnosis of our medical purposes. So, but we cannot see those radiation in our eyes because it is beyond our visible range. So our visible range is 400 to 700, and then even if we divide more into this visibility, the range, we'll see, you see that we have this within this small visibility range, we have different color: green, yellow, red, blue, violet. All those, the color we have, we can differentiate, our eyes can differentiate only in between this color, and then yeah. So using this color and using the wavelength, we can find out what is the color or what can be the color of that substance. But how can we actually use this different type of wavelength to analyze or detect some kind of compounds? For example, we see that if we burn something on a flame, right? We burn something on a flame, it will have some different type of characteristic color. If we burn a paper, it will have probably a yellowish color. If we burn some plastic, probably it will have an orange type of flame. The flame color will change, right? So, it depends on what type of material we are burning, and that material, it actually depends on the material's ability to absorb the photon or light or wavelength, and then that photon or electromagnetic radiation that is coming out when it cools down. So one thing is, this is any burner, this is a gas burner in our lab, but any burner, and then on this, actually it's a Bunsen burner. So on this Bunsen burner, there are the flames. If we put sodium, we'll see yellow color. All right, in our eyes, we'll see that the flame color becomes yellowish, right? Bright yellowish. If we put strontium, we will see scarlet color. That is quite, I think, red, yeah, a reddish color, something. And copper will give a green color, or not. Copper will not give. Rather that flame will. If we put the copper in the flame color will change to greenish or green. Same goes for barium, lithium, crimson. So what is actually happening? Why these different type of metals, all these are different metals, are giving us different color? Well, now it is the time to recall our periodic table knowledge. We have seen the atomic structure, right? At the beginning of our lecture, the atomic structure of different elements on the periodic table. The atomic structure tells us that since they have different number of proton and electron, their structure, atomic structure is different. Every one of them has a different atomic structure. The sodium, the potassium, that strontium, all those things. Just now we saw the previous slide. It has different atomic structure. Different atomic structure means they have different distribution of this electron around it, right? So when they have different electrons around it. So what is happening when we are putting this, let's say a small amount? Ideally, if we could put just one atom, it would be much more precise for us to understand, right? But it is almost impossible to put one atom exactly by using our human hand. So what is this? Let's say that we consider that all the sodium or all the potassium, all the strontium or whatever we are putting in the flame is very pure. It's 99.9999% pure. There is only sodium or potassium or only there, nothing else is mixed. So when we are putting this a little bit, a very small amount of sodium or potassium or strontium or beryllium, what is happening is all of them has a similar type of structure, right? All because we consider it's very pure form of that compound, and it has a very, all of them only potassium, only calcium, only strontium atoms are there. So all of them are similar looking, because similar thing. And then when we are putting these atoms in the flame, flame is energy. It is hot, isn't it? The flame gives us heat in the form of energy, right? So heat is coming from the flame as an energy. So that energy is being transferred to this atom of that different particles, or different elements. This heat energy is being transferred to these atoms, and remember that we are considering all the same atoms are there in the sample. When we are putting sodium, all around that is sodium atom only, nothing else. Sodium is not mixed with anything else, only sodium is there. So all of them are same. And then since they are same, they are all absorbing the heat from that flame, right? They are absorbing the heat from the flame. And what happens when we drink coffee or tea, right? Or some energy drinks, what happens? We become more energetic, right? We perform better, we run better, we play better, badminton, whatever you do, cycling, jogging, you do more because you have more energy in our body we have. So that energy is pushing, they are having more energy. That means that those energy is being transformed into these atoms, and then the electron start to jump to the next level, next higher level. The electrons, when it is not on the flame, when it is left alone, in the room temperature, just in the bottle, right? Let's say sodium is in the bottle. We are not disturbing, nothing. It's just like them. They are. So they are all the atoms of sodium or potassium or whatever. They are very in stable condition. They are not disturbed. So they are in their own environment. But when I put it in the fire or flame, everyone becomes excited. So the electrons start to jump to the next higher level, right? What are the higher levels? Why the electrons are there are levels? We discussed a very little bit about it, but probably we will discuss if we take more chemistry in the next degree. We will discuss more about it. But it will be okay for us to know that, okay, there are different levels that electron can stay around a nucleus in an atom. Around a nucleus, this is a nucleus, and around that there are electron, right? There are electron staying around it. So they can stay here, or they can stay outer side also. This is electron as well. This electron is the electron. So this line, just like an orbit, is shown that the electrons is about to somehow it's shown that the electrons is rotating in that way. in practice it is not the same thing, but it is good to understand that electrons are there. So there are other orbits or other stages that electrons can stay when they become excited. When they have more energy, they jump up to go there. All right. So when they jump, all right, they jump to that the next level by absorbing the energy. And then when the energy is removed, when we're taking up out from the flame, or not taking out, because once this jump, they cannot go beyond some certain stage, they have to come back to the original stage. So what is happening is when the energy is removed, they are coming back. The electron is coming back to the next, again to the original stage, or it is coming back to the original stage again. So when it is coming back, what happens is it cannot just come back because it did not go to the next level on its own. It was supplied with some energy. So what happens to that energy now? The energy, the electron must release. All right. The electron must release the energy so that the electron can come back to the original stage. When it is releasing that energy, that released energy comes to our eyes as a form of light, so that we see different lights. All right. And now you remember that I'm telling that sodium, potassium, beryllium, strontium, all those things, all them, copper, lithium, calcium, everyone has different structure, atomic structure. Of course, they are different. Otherwise, why they will be sodium and beryllium difference, right? Because they have different number of electron and neutron inside them. If all of them has same electron and neutron and proton, then there will be no difference. So since they are different, they will have different number of electrons and protons and all those things, and the different electrons will jump to the next different stage according to their structure, and then they will come back to the original stage by reducing or removing or eliminating different amount of energy. First of all, they need different energy to jump. Not everybody will use the same energy to jump to the next level. So they will need different energy to jump to the next level, and then when they come back to the same original level, they will release different energy. And different energy will give us different type of wavelength. And that wavelength is coming to our eyes as a different color. It's not that all the elements that are metal that we will heat up and then can see, because some of the wavelength it will not come to our eyes, but if we can see it, we will see the different color. Based on this technique, or based on this theory, one scientist came up with the idea that, okay, since they are absorbing different energy, since they are absorbing different energy to be excited, right? To be excited, and it is quite precise that, let's say that it is sodium. Let's say it is sodium, right? Let's say it's sodium. Yeah, it's sodium. And then it is absorbing this type of energy or wavelength. If I put this type of energy or wavelength, it will not absorb, or this type of energy or wavelength of energy, it will also not absorb. Only this type, certain type, or this certain wavelength of energy, it will absorb. So based on this, scientists came up with an idea that, okay, since they are absorbing different or certain wavelength, we can use the same technique to identify them, right? We can identify if there is a sodium or calcium or strontium in the sample. If we strike with the same wave, similar wave, exact same wavelength, that sodium will be excited, and we see in that sample there is some response, that means okay, in that sample we have sodium. If there is no response, so it's okay, there is no sodium in that sample. So this idea came to an the practice as atomic absorption spectroscopy. It is a destructive method of very sophisticated, very much reliable, but it is a destructive. That means if we use the sample, it needs a very small amount of sample, but the sample is gone. It will be destroyed inside the machine because the machine needs to destroy it to find out what is in the sample. So that is why it's called the destructive method. We cannot use that sample back. So metals and metalloids can be used in it, and if there is a higher concentration of some of the elements, we can reduce it or we can dilute this to get to the low concentration to do the analysis, because this instrument, this machine is a very sophisticated, and it just it's a ppm. Okay, it's a ppm concentration it needs, or it can read. So we do not have to give a lot or a huge amount sample, just a very small amount sample, or very diluted sample will also do. Okay, so how does it work? This is a hollow cathode lamp. Is there a hollow cathode lamp that can generate a different type of light pulse or different type of wavelength, and you can select actually that what wavelength you want. You want a sodium wavelength, or you want a potassium, calcium, iron, nickel, strontium, whatever wavelength you want, this hollow cathode lamp can produce. You just need to select it. And then the sample is fed into this burner, because the sample need to be vaporized, right? Vaporized means it has to be in gaseous form. If it's a liquid form or a solid form, the atoms are not going to absorb the light from the cathode lamp. So what it has to do is the sample has to be vaporized or atomized. So at higher temperature, the sample, a little bit of the sample is sprayed, right? I sprayed on the sample, so it immediately vaporized with this high heat burner. And then the light is absorbed by this vapor or atoms, and then the light passes through many processes, and then at the end it goes to the detector. So the detector detects whether which of the wavelength was absorbed, especially which of the wavelength was absorbed by the vapor atoms, and that is absent from the output of the wavelength. So from there, the detector tells us that in that sample, what type of metals are there. Okay. So you can go to this YouTube link to see the process more detailing it. One of the this is a very reliable and this is a very sophisticated process to find a sensitive process to find out the metal concentration in parts per billion. That is thousands of a million, hundreds of a million concentration. So that is even a small, very small amount of that metals. If it is in the sample, it can be detected. All right, it can be detected using this AAS instrument. So what are the some things that we can find in that? The arsenic, nickel, lead, mercury, all those, almost all of these heavy metals, right? The heavy metals are bad for health, human health, and it is carcinogenic actually. So to know, and this arsenic, if you have learned or if you have heard about arsenic, that it is it's a poison actually. It's a poison. It's a small. It's a very small amount if in the water it goes in our body. It is a cancerous. It produces cancer, and that's why it has to be detected. And in the water, actually, it is a very small amount, a very trace amount of arsenic is found, and in that trace amount, it is very bad for human health. So this is a tube oil. This is a tube oil, right? The hand pump tube oil, and it brings up the groundwater from the underground water, right? This underground water in Southeast Asia, actually, this underground water, northern part of Southeast Asia, this is quite much of the arsenic now. It is a big problem, and it is causing a lot of human health issues there. So what there are some NGOs, they're working tirelessly to make awareness in the people. And if you can see, this tube oil is a red color. This part is red, this tube oil. So whenever they detect that there is an arsenic in that groundwater, or this tube oil has pumped up arsenic, the water containing arsenic, so they will put this red color to mark that it is dangerous to drink. But with all these things, this arsenic is the good thing about arsenic is it only goes through our body by our digestive system. We can use this to take shower, to wash our dishes or clothes. There should be no problem. But only if we drink, that is a bad thing. So there is a mark, red mark is given on that. And also there is those who are in Malaysia, Kuching, you know that the Tasik Biru, right? Blue Lake, it has the arsenic concentration, very high arsenic concentration is 0.68 milligram per liter. So, and the WHO recommended is 0.01. So how many times it is? How many times? It's 68 times, is it? More than who has recommended us to drink. So that is why the Tasik Biru, I have been to there many times, and I see that usually, people do not go there. It's for recreational purpose. It's not a very big lake, but I have seen that some people are catching fish there, and I'm scared, I am worried actually that the fish will have a high concentration of arsenic that can go to our digestive system as well if we consume that type of fish. Now, okay, so now come back to that AAS thing, absorption spectroscopy. If we interpret the absorption spectrum, right, of a seawater, that in seawater, there are so many different elements or substances dissolved in seawater. So if we do some testing using the seawater and do it on the AAS, atomic absorption, we see that there are two different wavelengths, that calcium and sodium. We find that calcium is here. This length is telling us this is the calcium, and this one is telling us about sodium, the spectrum, right? But the problem is, there we know that in that seawater there are nickel and cadmium, both are there. And nickel and cadmium has a very close absorption spectrum. Very close absorption spectrum. So how do we find out what is, and chromium is here. Chromium is around 360, can say that is 360 nanometer. It absorbs the light. And cadmium absorbs around 200, let's say 30, and 240. Maybe the nickel we are absorbing. So if we add, if we try to do the analysis using a spectrometer, we will not be able to find out the cadmium and nickel concentration are in the sea, in the water. But if we use a different hollow cathode lamp that will produce different wave spectrum of light, that I want a 230 spectrum, another one I want 240 spectrum, they can produce exact amount, right? They can produce that amount. So if we do this, we will find how much cadmium and nickel is in the sample. Also, we can find how much chromium in the sample if we find out, if we have used a cathode lamp that produces 360 nanometer of wavelength of light. Now we are going to an example that says that iron is essential to our human health, and to determine the iron content in a flavored milk drink, 5 milliliter sample was diluted to 50 milliliter. 5 was diluted to 50, that means 10 times dilution, right? The absorbance of the diluted solution and of several standard solution was measured using AAS, atomic absorption spectroscopy. The results are shown in the table below. So what is saying that the sample, the milk sample was diluted 10 times, and after it has been diluted 10 times, a little bit of the sample was taken and absorbed. But before that, I want to know the iron content in my milk drink. So what I did is, I just don't want to know whether there is iron or not. I want to know how much iron is there. I already know that there's iron, but how much iron is there? So what we have to do is calibration. I have to do the standard run. All right. So how do I do the standard run? First of all, I took a 0.00 concentration of iron. How can we make 0.00 concentration of iron sample? That means it is just water, pure water, there is nothing else. This is pure water, nothing else. And then we took the absorbance in the instrument, right? Okay, this is the instrument. I took just water first. I put it here in there. There is no iron in the water. And then I took the absorbance. After that, I put one sample, all right? Standard sample 1, and then I got the absorbance. Then I put sample 2 and got the absorbance 3, 4. So like this. And sample 1 means 1 ppm, that is I prepared by myself. I calculated, I took iron, I measured accurately, I prepared the sample accurately. I know it's very clearly, I have done it very and sincerely, and I have what do you call it? I have done this experiment by myself, so I'm sure I calculated it myself. So I prepared the sample. I know that I have prepared 1 ppm, 2 ppm, 3 ppm, 4 ppm sample, right? And then every sample I put in the machine, I took the absorbance. I recorded the absorbance that has been recorded by the instrument, the machine. So for water, when there is no iron, I didn't put any iron. I took the water from the lab, is distilled water in the lab, but still I got some absorbance. Later I will discuss what happens. And then for 1 ppm, when I prepared 1 ppm solution concentration, then I took the absorbance, it is 0.08 I found, and then it is 0.15, then 0.22, 0.29 in that way. After that, I took the sample, so I found the absorbance for my sample, that is the milk, which is 10 times diluted, 0.19. All right, 0.19 absorbance I found. Okay. And now I want to find out what is the concentration of iron in my milk, the milk drink. So I plot a graph using all the standard samples I had. So at 0, there is 0.1 concentration in ppm. I took the first one was 0, right? First one was 0 and the absorbance was 0.1. So I put at 0, the absorbance was 0.1. 0.1 is here. And 1 ppm, the absorbance was what? 0.08. So it should be a little bit less than 0.1, is 0.8. So, okay. Let's say it is here 0.8 and then it is here, right? So on for 2 ppm it is 1.15. So for 2 ppm, I put the marker here. For 2 ppm, okay, so I put a mark here, right, like this way. All those samples, the graph I prepared in this way. Now, for my unknown sample, I do not know how many concentration, but I have the absorbance is 0.19. So absorbance is 0.19 and I make a straight line through, before that actually. So all 4 or 5 samples, standard samples I put, and then I join them with the line. This is the line I join, not necessarily join, but the closest line I can draw connecting all of them. All right. And now the unknown sample, my mix sample, that is 0.19 milk absorption reading it gives. I make a straight line on that, the tangent on the standard curve, and then I put a drop down list. Hello. Hi. Put a drop down list on this solution concentration axis. All right. So we get the concentration at 2.75 ppm because I drop down it here on this axis, which is a concentration, and the axis, the line touches here, which is 2.75 ppm. So 2.75 ppm, and it was 10 times diluted, right? So 2.5 ppm is the diluted solution that I diluted 5 to 50 milliliter. But when it is undiluted, so I have to multiply with the factor, diluted factor, that is 10. So it becomes 27.5 ppm in the undiluted sample. All right. So it is a simple math that what mass of iron would you consume in a 250 milliliter glass of drink, the recommended daily allowance of iron for people over the age of 11 is 18. What percentage of your daily dose of 250 milliliter glass of this drink provide? So if it is so, in my drink it is 275 ppm, 27.5 ppm of this iron is there. How much in a 250 milliliter dose of glass of milk will give you? So it's just a if we multiply this one, we get 6.87 milligram in 250 milliliter, right? And 6.17 out of 18 is just a 38%. So if we just drink 250 milliliter glass of milk in morning, like in the morning you drink 250 milliliter in glass, right? One glass. So you are actually taking a 38 if in your drink is that much of iron is there. So you're taking actually a 38% of your daily dose. So the rest 62% you have to take it from other foods. You have to meet it up by your other food. It says that why the water, even though there is no ppm of concentration, give us an absorbance of 0.01. Probably the water was contaminated, or a trace amount in our water, the supply water, right? Our tap water, it is treated, but it's some of the things that is maintained, like iron, sodium, those things are maintained in the water. Fluoride is given in the water as well. So that is why there are still a little bit of iron in the water is there. Suggest why the sample of the drink was diluted in order to measure absorbance. All right. Why was the milk diluted? It was diluted because if it is, it has to be within the range, because we have done the dilution, calibration. We took 1, 2, 3, 4, 5 ppm, right? So if it is, let's say, if we did not dilute and the sample, the milk sample would come here. Let's say that we just had 0.1, 0.2, 0.3, 0.4, no, 0.1, 0.2, 0.3, around 0.3 until 0.3 that concentration standard we prepare. But let's say that we did not dilute the sample and we get a reading or absorption about here. Or let's say we this line here and we get a line, absorbance here. So we have to draw this line here and bring down. But it is not calibrated beyond this range. It is not calibrated. Okay, beyond this range, it is not calibrated. Only until this range, this curve is calibrated. So if you do until here and take a reading and try to find out what is the concentration, probably it will be correct, probably it will not be correct, we do not know, but it is not accepted because it is beyond the calibration factor or calibration range. All right, so now the question is why the color that we see, why do we see a color? Why do we see this paper is white? Can anybody tell me why do we see this paper is white? Why don't we see the paper? There are yellow, red, green, black, different type of paper, but why this paper is white in our eyes? Can anybody tell? Want to try? Okay, because of the amount of light it reflects onto our eyes, close but not June. Okay, not very. Uh, I appreciate your answer because the amount of light it reflects into our eyes quite close, quite close. I just give some time for others to scratch your head and try to answer the question. By this time, I go get my cup of tea. Yeah. Yes, yes, of course. I mean, light means photons actually. I mean, light has dual nature. Is at the same time it is wave. It is at the same time it's particle. We don't go to that far, but we just consider that light is something wavelength. Let's say for us, wavelength will do very good, right? Wave. Light is an wave like this. Okay, so please think, try to answer if you want. There is no marks on it, and I will not scold you or anything if you have a wrong answer, but it would be nice to see what you think. And by the time 2 minutes, go get your tea as well. All right, I'm back. So I don't see anybody chipped in anyway. Okay, so why do we see color? Yes, the light has to do everything with it, but another thing is our ability to see the color. by our eyes, our human eyes. Okay. So as I said that our human eye only can detect or can see anything within this range of 400 to 700, right? 300 to 700, 400 to 700. Okay, so go to the back one sometimes. Okay, so 400 to 700, only this 300 nanometer distance, I mean range. 400 to 700 is 300 nanometer distance, I mean a range, right? Within this range, we can see the cats, dogs, or other nocturnal animals. They can see beyond or before this range. So how do they actually, I mean, what do they see actually? We cannot, we do not know. I don't know whether human will ever know, but I think there are some theories that how animals see things. But for us, we cannot see like them, we cannot hear like them. So only 400, and this 400 to 700 nanometer wavelength, there are all the 7 lights that we say, right? Visual, that violet, blue, then green, yellow, red, all those things in our eyes within these 300 ranges. So for this case, when we see a blue copper 2 ion actually in the solution, copper 2 ion solution in that beaker, this is blue because it is absorbing a certain wavelength of light, that and the rest of the lights, it is not being absorbed by this solution, and that is why we are seeing the color blue. So it is absorbing certain type of light, not all. For this case, the white paper, just now I told you, right? It is not, it is reflecting, it is reflecting all the lights at once. And that is why we see it white. And when we see black something, that means it is absorbing all the lights. And that is why it is black. All right. Okay, so have you heard, I mean, you must have heard about the black hole, right? That absorbs everything, even light is trapped inside. So, okay, now that is the thing, that it is absorbing a certain type of wavelength, and the rest of the other light is not being absorbed. And that is why our human eye only detects that one was not absorbed, and the mixture of those has not been absorbed. So we see the color based on that. Another thing is when some object is absorbing some kind of light, some wavelength of light, our eyes see exact opposite of that wavelength of light. I'm coming there actually. So simple colorimetry, we can say that if we take this copper 2 ions, copper ammonium, all right, ions, and the different concentration in a transparent glass bottle, or in a glass vial, that transparent, that light passes through, we will see that the higher the concentration, the higher the number or the higher the concentration, higher the blue color or the darker the blue color, because it is absorbing more of that light. So when the concentration is reducing in this way, right? Concentration is of that copper ammonium is reducing in this way. So when it is reducing in this way, that means we are going to more towards from dark color to whitish color, right? So that means it is, rather than in this side, it is absorbing more, but this side it is emitting more. It is not as it is most of the light is being transmitted through from this let's say this is number 1. From this number 1, most of the light is being transmitted, is going through one side and coming out from another side. But for this case, for number 2, it is going from one side, but not all of them are coming out. Maybe a little bit of it is absorbed from here. So that is why it is more dark than this side. And based on this technique, there is another type of absorption, spectroscopy was developed. It's called UV spectroscopy, UV visible, in fact. So this spectroscopy takes the range from UV until visible range. So all this bigger range it takes, and we can actually select at what wavelength we will be using the monochromator wavelength selector. So the light source is there. It produces light of different or very wide range of nanometer of lights that is produced. But with the help of this monochromator, we can select what wavelength or what range of wavelength should we be using for detecting our sample. So this is one technique that is non-destructive. The sample, we do not need to put anything in the sample. We do not need to throw the sample. We do not to burn. We don't need to burn the sample. We can use this sample and here detect it and then can use it for further analysis. So this is a non-destructive process. UV visual is a very fast and non-destructive, as I said, and can detect color compound and organic compound with conjunction with low concentration. Okay, but only thing is it has to have some color. If it is a very low, no color, it will not detect anything. It will not give us anything. All right, so the usage is versatile, and then quite many usages has, like in the clinical analysis, right? The hemoglobin, the sugar content in the body fluid, urine, the blood in urine, or many things. That dyeing process, the levels of nutrients in foods and other energy drinks, and many things. It can be, it is used for. You can go to this RSC, that's Royal Society of Chemistry, for more information if you want to know more information about it. All right, so now it is here that why do we exactly see that color that we see? For example, a commercial food dye. A commercial food dye, because of its character, we do not know what is the food dye. It should be a very big molecule, not a small molecule. It's a big molecule, and it absorbs a light. The maximum absorption happens. Why maximum absorption? Where is the, why does the absorption happens? Can anybody tell me why does the absorption happens? Chelsea says it is the wavelength absorbed. Yes, I think we discussed already, right? So can anybody tell me why some compounds or something will absorb light? Why would it absorb? Can anybody tell me? Can anybody answer the question? If not, then I'm going to call everyone one by one. If somebody does not give me any answer, I will start calling. So who wants to volunteer for your friends? At the beginning of this lecture, I actually talked about it. So I just want to see whether you can relate it or not. the frequency. My question was, why something would absorb the light? Why something would absorb? For example, here, why 428 nanometer? Why not 550 nanometer? Because it is a peak here. That means it absorbs a light at 400 maximum. It absorption happens at when the light reaches to the wavelength reaches to 428 nanometer. We started from 350 nanometer. The light, right? The light, the wavelength is increasing, and then when it reaches to 428 meter. 428 nanometer, then the light, the absorption jumped up. Suddenly the absorption, the compound started to absorb more of the light. But 550, 600, 700, 800, why it is not absorbing? So can anybody give me an answer? Attraction to electron. All right, close. Anybody wants to chip in? Lynn, are you there? Lynn. Okay. Chamad, any idea? Chamad. No? Erlin, you were typing something. Can you just unmute yourself and tell? Because the frequency doesn't match. All right. Okay. So at the beginning, I was telling that they have like sodium, potassium, magnesium, iron, then bismuth, or all those in the at the beginning of the lecture. There was a slide, right? So they are absorbing different lights, different wavelength, because at that wavelength, they are going to, because of their structure, at that wavelength, their electron are being jumped to the next level. Okay, at that wavelength, they are not going to take any other, because it does not. Yes, attraction of the electrons. Yes, nor says so. It is. I guess you try to mean that, but if you provide answer in this way in the exam, you are not going to get any marks, because it does not clarify, or it is not clear. It does not. I don't know. I mean, convey the message that you want to try and give. Chelsea says that the frequency. All right, the frequency is partially true, but is not true, so you are not going to get the marks as well if it is in the exam. Erlin says the frequency doesn't match. Yes, but it also does not. Frequency doesn't match with what? You have to mention that term too. So let's come back to this problem, that the interpretation of the absorption spectrum, that the material, the food dye, is excited only it is only excited at 428 nanometer. None other wavelength excites it that much as in 428, right? Why it is excited? Because of this structure, atomic structure or molecular structure. So this is the reason. And then if we see the color or the absorbance is happening at 428, this is the color wheel. According to the color wheel, we will see where it falls, right? And the color wheel is increasing in this way. Increasing in this way. We started from 400, 450, 495 here, then 600, 590, 600, and then it goes out in this way, increase in this way until 800 nanometer. That is the maximum that you can, our visible range, right? 780. So at 428, so it will be 428 something here. 428 something here it will be, because 400 is here and 450 is here, so 428 should be in between here. 428 something like that. Something is here at 428, right? So if it is 428 here, our eyes or we will see the color exact opposite or in according to the color wheel. Exact opposite according to the color wheel, exact opposite. Okay, let me see if I can draw a straight line. So the exact opposite of 428, oh my God, will be here. Yeah, it's quite good. So we will see it is yellowish. Yellow color, we can say that, yellow to green in boundary, like that. Okay, and if it absorbs a wavelength of light which is like, let's say 500 nanometer, let's say it's 500 nanometer here, right? Because 495 here is 570 here, so let's say 500, let's say it's 520 to be more precise. Is 520 nanometer. So our eyes will see the color is red. It is, our eyes will see the color here. This is our eye, okay? This is our eyes. So we will see the color here. So whatever wavelength it is absorbing, our eyes will see the opposite color according to the color wheel. Right. Now let's say that identify what color will be exhibited by chlorophyll. We all know chlorophyll is in the plant, right? Plant leaves. Explain your answer based on the lambda max displayed, and then suggest a wavelength which is suitable to use in analysis, analyze the concentration of chlorophyll using calorimeter. So we see that the chlorophyll is absorbing two different light. I mean, it is absorbing two different wavelength of light, not single, but two different wavelength of light. So 420 nanometer and 660 nanometer. 420 and 660. Now, if we, this is actually the color wheel expressed in table form, but color wheel for me, I think it is better to understand. So 425 and 660. So now let me erase it first to become clear. 425. Where is 425 here? It will be 425 around here. Let's say around 425. No, it should be around here because it's 400 in the middle. 425 nanometer is just in the middle. So it is absorbing for the chlorophyll one, right? is 420. So it is absorbing the violet light 420. So 380 to 450. So it will be violet region 420 nanometer it is absorbing. And 660 nanometer, it is here. 660 it is red. The 660 it is absorbing in the red light area. So 660 it is absorbing, let's say it is here 660 nanometer, right? Now there are two color. One is green, another one is yellow, right? So these two color will be corresponding to our eyes. It is interesting now. So which color do you see? Can anybody tell me which color do you see for chlorophyll? Green. Chelsea, why is there is a note of interrogation at the end? You are not confident what the plant looks like? So only Chelsea knows what the plant looks like. Others have never seen a plant. The leaves. Not confident? Why? You don't eat veggie as well, yeah? Need to eat veggies, okay? So this is green color that comes to our eyes. Why? Why not yellow color comes to our eyes? That is a different, a different discussion, but for your understanding or for your convenience, I just want to say that human eyes has some, a structural thing. I also don't know much, but I know this much that human eyes detect the green color from far better than any other color. Okay, it detects more during the daytime. It detects green color better than yellow color. So our eyes, green color. I mean, in a very layman form or in a very simple form, we say that okay, we see green better or more than any other color, or our eyes is feels easy to see. That's why we see green. Actually, sometimes if you look at it very closely, you see that the color of leaves, it is changing the color. I mean, okay, it's complicated, right? I don't want to make it complicated, but because green is easy for our eyes to see, that's why we see green. Okay. And then at what color, I mean, what wavelength will it be easier for us to detect chlorophyll if in a mixture of a sample? If in a mixture of sample we have, what is the color that we can detect chlorophyll? Either 420 or 660 nanometer, both are okay to detect if there is chlorophyll in the mixture or not. Another problem is here that alizarin dye, all right, is used as acid-base indicator. In acidic solution, it is one color, while in basic solution, it changes its structure change, and as a result, its color change. Curve A is the acidic form of alizarin, and curve B is the basic form in the above absorption spectrum. So what color will we see for acidic medium and also for basic medium for alizarin? It's just like phenolphthalein, right? We have used phenolphthalein for our titration. So it is also like phenolphthalein, another type of, just another indicator. chemical indicator that we use for titration can be used for indicator. So in it changes color just like phenolphthalein changes color. So in acidic medium, it is the curve A, right? Curve A in acidic form. So this one is acidic form, curve A, acid, and B is for basic medium or alkaline medium. So what color should we be seeing in our eyes for curve A, acidic medium? Here it is absorbing 450, 440, 445 something. And for B, it is absorbing, the maximum absorption occurs at 570 maybe. Okay, or 580, something like that. 575. 575 for alkaline. So it's 575. It's already given here, but if we want to understand how it's 575, it is here. 575. It is absorbing the yellow region. So we should get the opposite color will come to our eyes, which is violet or purple color we'll be seeing. And for acidic medium, it is absorbing 440, right? So it is 440 like that. Here it is 440 is here maybe. So we will see it orange color. To our eyes, it will be orange color. Orange color we will see in our eyes. Dopamine. That is the drug that is used for Parkinson's disease. And this dopamine is actually, okay, it if we do exercise, right? If we do exercise, physical exercise, run, do any other physical exercise, it secretes in our brain. We don't need to take it. We don't have to be worried about taking them. So it's to be active. If we are active physically, then this dopamine comes naturally. It's produced naturally. Okay, so this dopamine actually is used to treat, it has a 280 nanometer lambda max. That means at 280 nanometer, it will absorb the most of the wavelength. And the higher the concentration, the higher the absorbance peak we will get. All right. So now the question is telling us, what is that? And that is how we can find out, quantify the dopamine. So first of all, we will take a known concentration of dopamine, like number 1 here, then number 2, then number 3, number 4. We will take number 5, and if you want to make more, we can make more. And by this way, at single wavelength, at the same wavelength, different concentration of dopamine, we take and we do the calibration curve, right? We do the calibration curve, and let's say that this is this is something that we do not know in our drug, that there is dopamine, and we do not know how much it is. So it gives us a concentration of here, something like that, right? Something like that. It is 6, 8, or maybe it's 8.5, 0.85, something like that. Constant, the absorbance, the peak absorbance we found 0.85. So from there we can find the quantification of the dopamine. Another question it says that the concentration of iron in a sample of dam water was determined by UV-Vis spectroscopy. Iron present as iron 2 was in the sample and was reacted to form an orange-yellow complex. All right, this is important. If it is iron 3, it will be, if it were iron 3, it will be colorless. Sorry, iron 2 was iron 3 is colorless, so iron 2, it will produce some color. There are two forms iron can be formed, iron 2 and iron 3. Iron 3 is colorless. If it is in the water, we will not be able to see, but iron 2, it will give some orange-yellow complex. And then we can use this, because of this color, we can use the UV visible spectroscopy to find out if there is iron and how much iron is there in the sample. Okay, so likewise, we do the calibration curve. We produce some sample. We take 4 microgram per liter per milliliter, or 4 milligram per liter, 4 ppm sample, 8 ppm sample, 12 ppm, and all these things we prepare in the lab. All right, we took the water in the lab, that is the water, that means the distilled water. Those who are coming back to lab, you will see the distilled water, and then I add iron 2 inside that water to prepare the standard sample. So this is the calibration. By this way, we produce the calibration, and this is the calibration curve. And then iron sample, where is the iron sample? The absorbance, the sample gives the absorbance of 0.38. Okay, the sample is giving the absorbance as 0.38. So this is 0.38. From there we see it is 9 microgram or 9.9 microgram per milliliter of the absorbance of the sample we have, of the iron we have in the dam water. So from there, actually, we can find how much in per liter. Okay, it is in milliliter. So how much per liter, how many milligram, or whether it is according to WHO standard or not. All right, WHO means World Health Organization. It is safe to drink or not. All these things we can find by this from here. Now the last example here, it says that the tartrazine, a yellow food coloring, right, agent in jelly beans, is analyzed using UV spectrometer. The mass of beans was weighted and found to be 3.2 gram. Mass was found to 3.2 gram of the jelly bean. The bean was then dissolved in a suitable solvent mixture. We have to dissolve it because UV visible cannot do measure of that solid particles. Okay, and this procedure will dilute. It was dissolved in the solvent mixture, and that procedure actually dilutes the tartrazine in the jelly by 10 factors. So that means when we produce, when we dissolve it in the solvent, we actually make it from solid to liquid by that way, but also we dilute by 10 factors, like 10 milliliter, we produce 100 milliliter, like that. And at 410 nanometer, we standard, we ran at the same nanometer, because this is the light, wavelength of light that tartrazine actually absorb most. And then the diluted bean sample was then eluted and absorbed and was found to be 0.3 nanometer. So it was 0.3 here, right? drop down on the x-axis, that is concentration axis, and we find it was supposed to be 5, 6, 7, 8, 9. Yeah, so it's around 7, probably around 7 ppm, milligram per liter. So 7 ppm it was, and then you remember that is 10 times it was diluted, so it is 70 ppm or microgram per gram. So 1 jelly bean was 70 microgram per gram, but 3.1 jelly bean was 70 microgram per gram. The tetraxine was there. So 3.2 jelly beans will be how many gram? That is 200 times 3, right? 3.2. So it is giving us 224 microgram of tetraxine, which is mass percentage is 0.007. All right, because 224 microgram, that means 10 power negative 6th of a gram in 3.2 gram times 100%, so it's 0.002. Sorry, 0.007 microgram. It is actually in the percentage of weight percentage by mass percentage of tetraxine in sample. So this is the end of it. This summary is given here. So do you have anyone has any question? Anyone has any question? Lynn says no. Good. So now that is it for today. But Chelsea says no. So I'll say that, can you please go to this lecture slide? Lecture slide, what is the name? Wait, the number is, okay, is number 5. Lecture slide 5. This is the Einstein's equation, right? And E equals h nu. H is the Planck constant. Planck constant. Planck's constant. Max Planck, the guy who also helped to develop the quantum mechanics. And then nu, this is nu, is equal to C over lambda. C is the wave, speed of light, that is 3.8 times 10 power 6 meter per second, I think, if I'm not mistaken. And this is the wavelength. Okay, the wavelength of that. So if we know the wavelength of certain light, we will find the nu, right? And then this nu, we can use it here to find out the energy of that light. If we know what is the Planck constant, right? If we find out the Planck constant, if we know what is the Planck constant, then the nu, then we will find the energy of a light. And this Planck, there are many Planck constant. I mean, there are different forms of Planck constant. For us, we need one that is meter per kg per second, meter square per kg per second, which is usually, I don't know if you can see in this way, yeah, 6.6 to 607 10 power negative 34 per meter square kg per second. All right. So this is our, so based on this, please write it down on your paper, because we are going to the Menti question now. Write these two equation down. Equal to MC square. I don't know. I don't know. That is different discussion. Yeah, equal to MC squared. We don't discuss now. So, but this is also quite important actually. Einstein got the Nobel for this equal to h nu, not equal to MC squared. So this. Okay, write down this equal to h nu and nu equals c over lambda. Okay, c over lambda, that is the wavelength. And then please go to menti.com. Menti.com and then use this code 92580815. Okay, so use this and then please vote. And this is the open. As long as you need, you can vote. No problem. And this is it for today. I will see you next Thursday during the lab. So all the best. Take care. Thank you.